Today's seminar is by Andy Neitzke, and as you can see, the talk right here is differential equations and deformations of quantum field theory. So that sounds very exciting. So please, Andy, go ahead.
Thank you for the introduction, and thanks for the opportunity to speak in this seminar. So as the title suggests, this talk is about some relation between, on the one hand, quantum field theory, and particularly supersymmetric quantum field theory, and on the other hand, the theory of differential, I guess, linear differential, and more recently, linear difference equations. And so it's a story that's been around for a while now in some form, and so I'm going to review part of the basic story, maybe say it in a way a little different from how it's usually said. I'll give some updates, and toward the end, I'll say some very speculative things, which of course are the things I'm most excited about. It's a subject that has been influenced by quite a lot of people, including many of the participants in this seminar. So I think that some of you are much more expert than I am, and so I hope you'll, I hope I'll learn something from your corrections as I go on. Most of what I know about this subject I learned from starting with joint work with Davide Gaiotto and Greg Moore, more or less on quantum field theory side, and then subsequent joint work with various people. So Chris Beam, David Benzvi, Matt Bullimore, Tudor Dumofte, David Dumas, Laura Fredrickson on the math side, Alba Grassi, Chen-Yu Hao, Lotte Hollins, Ali Shepper, and Fei Yan. Okay. So my starting point for this talk is going to be a quantum field theory, what's called a four-dimensional supersymmetric quantum field theory with so-called n=2 supersymmetry. And the standard example of such a theory, which you might have in mind, is the theory that was not introduced by Seiberg and Witten, but was famously studied and in some sense solved by Seiberg and Witten, namely supersymmetric Yang-Mills theory with gauge group SU2. But we're not going to study the four-dimensional quantum field theory just by itself, as Seiberg and Witten did back in 1995, but rather we're going to introduce another element. We're going to introduce a two-dimensional defect sitting inside of the four-dimensional quantum field theory. So we're studying a kind of coupled 2D, 4D system. Sometimes it's called a surface defect. And that should, again, be preserving some of the supersymmetry of the theory. So it'll preserve what's called n=2, 2 supersymmetry. And one special case, which is kind of useful for calibrating your your thoughts about this stuff, is the case when the four-dimensional theory is actually trivial. So then a defect just means a two-dimensional theory with n=2, 2 supersymmetry. And that's a very well-studied area, and so a lot of things that people know about that become relevant here. Now, in many quantum field theories, there are couplings that are adjustable, and that's the case here. I'm not going to talk for a while about the couplings of the four-dimensional theory. I'll think of those as being frozen until the end of the talk. But I do want to talk about the couplings of the two-dimensional defect. So we've got this 2D defect living inside of a four-dimensional theory, and there's some adjustable couplings on the defect, and they generally sweep out a moduli space. I'll call it C, which is complex analytic, roughly complex manifold. Okay, so that's our starting point. We have a space of couplings, which is a complex manifold C. Now, there's a dictionary which connects that situation. So my situation is this 2D, 4D coupled quantum system, which connects it to a linear ordinary differential equation living on the parameter space. Or better said, it's a family of them for two reasons. One reason is there's a small parameter epsilon, which is going to be important in what follows. And second of all, there are also some of the coefficients of the equation can vary. That's because the four-dimensional theory has what's called a Coulomb branch. So this is a dictionary. Anyway, so some dictionary between, on the one hand, these surface defects in four-dimensional field theories, and on the other hand, linear ODEs defined on some complex manifold with meromorphic coefficients and with a small parameter. That's been, in some sense, it's been discovered several times by several different groups, particularly by Nickerson and Jeff. All right, so what are some examples of this? So I said there's some dictionary between quantum field theories and differential equations, so I should tell you at least, what are a few of the basic examples. So for the field theory that Seiberg and Witten studied, the corresponding equation is what's called the Matthew equation. It's a Schrodinger equation with a periodic potential, but now we analytically continue it, so allow the coordinates to be complex. More recently, so that example has been studied a lot from various points of view. More recently, Fei Yan studied the analogous thing for the group SU3. Then you meet, instead of a Schrodinger equation, a second order equation. Here you meet a third order equation, which I thought was interesting enough to actually write the form of the equation. So can you see my mouse pointer as I move in here?
Yes, sorry, I was muted. Yes, we can.
So it depends on these parameters. As I said, it's some parametric family of equations. So it has this U1, U2, and lambda, a small parameter epsilon. So anyway, some third order equation in the complex Z plane with singularities at 0 and infinity.
And Andy, is epsilon supposed to be small in?
I mean, epsilon in the actual story, epsilon is some finite. It doesn't have to be small, but we're going to study things by perturbation around epsilon equals 0.
Yeah, why is there a reason why you wrote this equation in this strange way with epsilon -1 and not, as mathematicians get used to, with epsilon cube d cube? Because
let's see, did I make a typo here?
No. It's certainly it's intentional. I mean that normally when mathematicians just a small remark when they speak about equations.
Oh, you put the epsilon in front. You would multiply the whole thing by epsilon cubed.
Yeah, and then WKB is something which comes to the mind if you write it in this way. So it's kind of.
Yeah, I somehow got in the habit of writing it this way because I think of the epsilon as rescaling the differentials, like the quadratic and cubic differential, rather than rescaling the operator. But I agree. I mean, no, there's no fundamental reason, I don't think.
Okay.
Okay, just to go a little further, there's another kind of quantum field theory, a little harder to construct, but kind of well known, called the Argyros-Douglas theory. That one corresponds to Schrodinger equation with polynomial potential. Studied from this point of view by these authors. In a similar way, you can get a kind of higher order analog of Schrodinger equation with polynomial potential, where you have, instead of just the d by dz squared, you have d by dz to some higher power, and then you can have, so in between the highest derivative and the constant, there's a bunch of other terms with lower powers of derivatives here, all with polynomial coefficients. If you study the so-called Minahan-Nemeshansky field theory, it's a famous field theory because of the sort of strange fact that it has an E6 global symmetry. Then you get a third order equation with 3 regular singularities on CP1. If you study a pure 2-dimensional field theory, so remember I said a special case of this is to study just instead of studying a defect in a 4-dimensional field theory, to just study a 2-dimensional field theory. And their basic example is the Landau-Ginzburg model with some superpotential W. And then what you get is what's called the quantum differential equation. That's so I didn't write an explicit form of that equation, but you can write what its solutions are. Its solutions are these kind of exponential integrals. Okay, so those are the kind of equations that we're talking about.
I have a question.
Yeah.
So in SUN, Jan-Mills theory, Alva and I studied the quantization of the Seiberg-Witten curve, and we found a kind of difference plus polynomial equation. Is this equivalent to this SU3 theory?
So I think what that corresponds to is studying. I think in this language it would be studying.
Because the WKB expansion of our equation is actually the expected one. So we actually solved that equation. So we solved the spectral problem for that problem. But it was looked very different from this one.
I think that the story is that, of course, it's the same field theory, but a different defect.
Okay.
So one thing you can do, right, is in here I wrote defect. I didn't tell you which defect. But
Right.
in general, you can introduce all kinds of different defects in the same quantum field theory. And those typically give rise to, it's an interesting story here because they give rise to different equations, which nevertheless have the same Veroth symbols and so on. Because the Veroth symbol is something that's in the four-dimensional theory. So I think that's the answer to this question. Okay. And so on and so on. So there's many examples. Okay, so now I want to say what part of this dictionary actually is. And so let me just remind you, although I guess people here are experts. Let me remind you of the WKD method for solving one of these equations. So to be concrete, let's say it's the one of these Schrodinger equations here. Okay, here I did put the epsilon in front. So if you're given one of these equations, you can try to build the solutions by, well, you can try to do perturbation theory, but then the better thing to do is not just do perturbation theory, but do the Borel summation of the perturbation theory. And so you write down a formal perturbation series. For example, you might write it down in this kind of exponential form. So the formal solution is the exponential of some integral, and the integrand you expand in a series in powers of epsilon. The idea is that the leading term is roughly square root of minus p, and then all the higher terms get determined by plugging back into the equation. And in that way, you get some formal series solution. And that formal series generally has zero radius of convergence. So the way you try to make sense of it is by this procedure of Borel summation. Namely, this phi, I'll replace this phi, which is phi of I should have written here z prime comma epsilon. So it's phi of z prime and epsilon. I'll replace it by its Borel transform, where I just divide the nth coefficient by n factorial and change the variable. Now I call the variable zeta, coordinated in the Borel plane. You think of this as a kind of formal version of the inverse Laplace transform. Now then, if everything goes well, what you next want to do is to perform the forward Laplace transform of this, and hopefully that produces for you the actual solution that you're after. Now, the obstruction to doing that is that this b phi a priori, here I've defined it as some, I've just written a sum. That sum, hopefully it converges in some disk, but then you still have the problem of, in order to make the Laplace transform, you have to integrate not only over the disk, but over a ray, which goes all the way out to infinity. So you have to analytically continue this Borel transform along a ray from 0 to infinity. In the process of doing that, you may run into singularities, and the singularities are kind of the key thing in the story. They're responsible for the Stokes phenomenon. So what you find is that as you do this Laplace transform along different rays, in other words, for different phases of epsilon, you'll get local solutions which don't quite match up, because sometimes you cross one of these singularities. When you cross one of these singularities, you get a jump of the solution which is non-perturbative. It's invisible in the asymptotic series, but it's nevertheless important for the kind of global analysis of the equation. Okay, so this is part of the story that was developed by many people in the exact WKB community. And so, okay, so the key thing is these singularities in the Borel plane. So now here's kind of one basic entry in this ODE QFT dictionary. It's that those singularities, so that's something which you define completely in the world of ODEs. You're just trying to solve your ODE and you run into these singularities. The statement is that if you have a singularity which sits at some point zeta equals, I'll say zeta naught, that corresponds to something in the field theory. And what it corresponds to is what's called a BPS particle. So it's a particle which preserves some of the n equals 2 comma 2 supersymmetry. In particular, there are these absolutely stable objects in the theory. And the position of the pole, the position of the singularity, is what's called the central charge of the particle. Some complex number that's canonically associated to this particle. And in particular, to get some idea for what it is, the mass of the particle is just the absolute value of the central charge. So these singularities, in the exact WKB method, it's kind of known that the further the singularity is away from the origin, the less important it is. It creates a smaller it creates a smaller, a more exponentially suppressed effect. And in quantum field theory, that corresponds to the statement that the effects of massive particles are exponentially suppressed by their mass. So here the mass just is the central charge, which is the distance of the pole from the origin. And then you can go on and, oh, so I should say a few words about this. So this statement in concrete examples, like Schrodinger equations, this turns out to reduce to something that's, I only realized recently, this is actually written in the book of Kawai and Takei, in the appendix of the book of Kawai and Takei. They give a formula for where the poles should be, and that formula exactly matches with this statement. But in other contexts, this dictionary has been discovered by various people, including people here. So then you can go on and you can say, now there are various phenomena, such as you move around in the parameter space, in the domain where the equation is defined, the singularities can, in the Borel plane, can appear and disappear, and that corresponds to this phenomenon of wall crossing in the field theory, where one of the particles living on the surface defect can decay by emitting a particle into the bulk. It's called 2D4D wall crossing. In fact, even the Stokes phenomenon itself, for the solutions, you can think of as a kind of wall crossing in this in the quantum field theory. Another thing about this that I think is kind of nice, which I didn't appreciate until reading the paper of Grassi, Gu, and Mourinho, is that you can actually use this thing in practice to learn something about the field theory. Imagine that you are studying one of these quantum field theories. You want to know its spectrum of particles. That's one of the basic observables. One way that you can find it, according to this dictionary, is to write out the perturbative series that solves the corresponding differential equation. You can just write it up to some finite order, then make a Pade approximation of to the Borel transform, and look at where its poles are, and that actually gives you a pretty accurate measure of where the BPS particles are in this quantum field theory. At least the ones that are close to the lightest ones, the most important ones, you can actually concretely discover in this way.
Andy, excuse me, before you proceed, it's a mathematical question because I'm a bit lost. Are you trying to build this ODE QFT dictionary, or you explain the existing dictionary?
Right now, I'm just telling you some facts about the dictionary. I'm not yet trying to say why this dictionary exists.
So, but does it exist or not?
It has been
mathematically what you are saying. It's been known,
well,
with maybe with different names, but for quite a bit of time. Yeah. So you put just new names like BPS, like masses of BPS. It's kind of physics on the physics side. But is there a dictionary which kind of consistent and you can?
Yeah. So you want to know like what's the new mathematical statement that corresponds to this, right?
For example, yeah.
I mean, one thing you could say. So as I said, in the case of Schrodinger equations, the position of these singularities was at least stated in the book of Kawai and Takei.
Yeah, actually, I read it in the book of Carlos Simpson at the beginning of 90s. There is a kind of manuscript and lecture notes where he did it for Schrödinger and did it first for SL2, then for SL3. And he showed that these singularities are basically just images of the period map, which is a central charge. So it's kind of
right. So that's exactly what I'm saying here. Yeah. So then, okay. Actually, that's interesting. I didn't know that Simpson had said it also for the higher rank. That's one of the things I was going to say is that in higher rank, maybe the statement was.
He tried for I think for SL3 or for JL3. I should check. But he didn't go to an arbitrator. Yeah, JL.
I see. So one thing you could get from this is the analogous statement for SLN. Now it wouldn't be a theorem, but at least there's a definite statement about where the singularity should be for SLN. And from this framed wall crossing, you can similarly write down, you know, like as I think you know, you can write down formulas for what the Stokes automorphism should be. Like what's the jump that you of the solution that you get when you go across the singularity. So that's the kind of thing you can get from this. But for the most part, what I'm saying here is not really strictly a mathematical statement today, because one side of it is this quantum field theory, which isn't a completely mathematically defined object. Okay. So should I go in?
Yeah, thank you.
Okay. Right. So yeah, and okay, and as I said in answering one of Marcos's questions, so what I said so far had to do with BPS particles that live on the defect. There's also, in the pure four-dimensional theory, there are BPS particles, and those also show up as singularities on the side of the ODE. Now, not in terms of the local solutions, but in terms of these objects that are called the Gross symbols that you get by integrating the WKB series around loops. Okay. Okay, so what has this been used for mathematically recently? So one example of the kind of thing that you can do is you can fix the parameter epsilon and look at where the Stokes phenomena would occur in the parameter space. So knowing that they correspond to these BPS particles, you can draw a concrete picture of where the Stokes phenomena actually occur. And that gives the what people in tech WKB call the Stokes graph, or we call it the spectral network. So here's an example of one corresponding to the equation, the third order equation that I wrote here. And then so then you can use it for kind of quantitative analysis of the differential equation. For example, if you want to calculate the Stokes data or the monodromy of this differential equation, you set up a kind of analog of the exact WKB method here for SL3 instead of SL2, which is for rank 3 equations. And so you can determine, for example, like asymptotic expansions of the Stokes data around epsilon equals 0. Or you can write down integral equations that the Stokes data satisfy. Now, for rank 2, these kind of statements are theorems. For the higher rank equations today, they're not theorems. And the main reason why not is that when you write the WKB series that represents the local solutions, so in rank 2, it's known to be Borel summable. In higher rank, it's not known to be Borel summable. On the other hand, you can just assume that it is Borel summable and then work out what would be the corresponding predictions about the Stokes data. Then you can go and test those predictions, and the predictions in every example that we've tested, those predictions do actually work out. So it looks like the higher ranked WKB theory is going to be quite parallel to the exact WKB in rank 2.
So a question, do we expect higher Chevret classes for the higher ranks, or are we still just expecting them to be Borel summable?
Yeah, I think it's still Borel summable in the same way as it is. If you look at it as a function of h bar and the expansion in h bar, then I think it's Chevret 1, just the same as for the rank 2.
So h bar is epsilon in your notation?
Sorry, yes, absolutely, yes. H bar is epsilon.
Must be.
Yeah, that part is not different.
Okay.
Okay. Now, so in doing this kind of analysis, you're limited a little bit by the kind of geometric complexity of the Stokes graph that you encounter. So I said that in higher rank it's parallel to what happens in rank 2, And for the formal structure, that's true. But on the other hand, the kind of combinatorics of the story can quickly get out of control for the higher rank examples. And so for this one that I showed you in rank 3 with kind of low order polynomials, there you can really carry out the analysis to the end. For the higher rank ones, it seems to be much more difficult. So I'll come back to that at the end of the talk. Okay, now I wanted to say a little bit about why this dictionary exists from a quantum field theory point of view. So there's one way to get it, which is a little bit indirect, which is you take your 2D4D system and compactify it on a circle of some radius, say radius r. And then you study the vacuum, the kind of ground state of that, the ground states of that system on the circle of radius r. Then you get a finite dimensional vector space, but more precisely, for every value of the parameters, you get a finite dimensional vector space. So what you get as you vary parameters is you get a complex vector bundle, the vector bundle of vacua of this surface defect. And then as Shakoti and Vafa studied a long time ago in the pure 2D context, that vector bundle is carrying a family of flat connections parameterized by a parameter zeta and C star. Now, those connections are somehow much more complicated than the ones that than the differential equations that I wrote at the beginning. But you're supposed to recover those differential equations if you take a limit, where you take the radius of the circle to 0, you take this C star parameter zeta to 0, and you hold fixed their ratio. And then that ratio becomes the parameter epsilon that we had before. So that's one way that you land on the ODEs that we're discussing. But it feels a little bit indirect. And in particular, one of the ways that this dictionary was first discovered was to take the 2D4D system, don't compactify it on a circle or anything complicated like that, but rather you're supposed to study a sort of circle equivariant version of the theory. So you have this surface defect lying on a plane inside of 4 dimensions, and you work equivariantly with respect to the rotation in the plane. And then you have the equivariant parameter for S1 called epsilon. And this is essentially what Nekrasov and Chatashvili were studying. And that's how they discovered this dictionary.
Because the sign is
What's that?
the new one.
Sorry?
Flip the screen if you want.
Can people mute themselves, please? We are hearing people who are not asking questions or anything. Are just people who have their microphone on. Please, I think Francois and...
Yeah, Francois David,
I see.
you have your...
Okay, never mind.
You're not muted. Thank you. He just muted you. So thank you.
Sorry.
Yeah.
So I wanted to give some indication of why is it that doing this circle equivariant version of a quantum field theory leads to differential equations. And so this is part of a kind of general story, which is that when you turn on this omega background, when you work equivariantly for a circle rotation, it introduces a kind of deformation quantization of all the structures, all the algebraic structures in the quantum field theory. And the thing that's relevant for us is kind of the simplest part of the quantum field theory, which is the local operators. So whenever you have a quantum field theory, you have this notion of local operator, which are the kind of defects that can be inserted at points of your space-time. Now, in a general quantum field theory, the local operators form some rather complicated structure, something like a factorization algebra. But in supersymmetric theories, you get something that's more tractable, and that's what I want to try to describe here. So one familiar example of this comes in 3-dimensional theories with what's called n = 4 supersymmetry. So so there, the space of local operators forms a representation of the whole superalgebra of supersymmetries of the field theory. Now, in particular, luckily we don't need the whole supersymmetry algebra here, but we just need to fix one supercharge, one odd generator Q, which squares to 0. And look at how it acts on the local operators. Well, in particular, so you have something that squares to 0, so you can look at its cohomology. And then that cohomology naturally carries the structure of, well, first of all, a commutative algebra. Why does it have the structure of a commutative algebra? It's just because when you have two of these operators inserted at 2 points, you can bring the 2 points very close together, and then from long distance, it looks like a single operator. And in these topological theories, the operator that you get actually doesn't depend on the position of the 2 points up to Q exact terms. And so you can bring them very, very close to each other. Just consider that to be a new operator. So in that way, you get an algebra structure. What's a little subtler to see, but it's also true, is that you get not only an algebra structure, but actually a Poisson algebra. And then when you turn on this omega background, that the Q cohomology gets deformed from a commutative Poisson algebra to a non-commutative algebra. Why is it non-commutative? Because after you turn on the omega background, the Q closed operators are restricted to sit at the fixed points of the rotation. So before we had operators which you could put in the whole R3. Now they're restricted to lie on the axis, a one-dimensional. They're restricted to lie on this copy of R, which is the fixed axis of the rotation. And in that case, there's two possible orders that you can put them in, and they can't swap orders without crossing each other. In that case, there's no reason why the product has to be commutative. Do you get a non-commutative algebra? So that's kind of the usual sort of deformation quantization. You start with a Poisson algebra and you get a non-commutative algebra. Now, okay, so that's the kind of familiar story that omega background gives you quantization. And what I want to say is that this this story of getting differential equations is also an instance of the same thing. You can think of it in the same way, except that instead of working in 3 dimensions, we now work in 2 dimensions. So let's consider again the quantum field theory living on this 2-dimensional surface defect. Again, we introduce a supercharge Q which squares to 0, and we take the cohomology of that supercharge acting on the space of local operators. So that gives us some finite dimensional vector space, and then as we vary the couplings of the theory, those finite dimensional vector spaces sweep out a holomorphic vector bundle over our parameter space. And again, much like I told you in the 3-dimensional case, we have, for the operators that lie in this cohomology, we have a natural commutative product, and it's just defined by, if I have 2 operators called O and O prime, the product of the 2 I get by putting one of the operators at 0, another of the operators at, say, z, and then take the limit as z goes to 0. And that product is commutative, or said otherwise, there's only one way of combining O and O prime to get a new operator, because the configuration space of pairs of points in R2 is connected. So any configuration can be reached from any other configuration just by
Andy, you go to the cohomology, and at the level at the level of complexes, do you have just an E2 algebra or something like that?
I think that would probably be the right thing to say. Yeah, is that here we have an E2 algebra. So before we had an E3 algebra deforming to an E1 algebra, and here we're going to have kind of E2 deforming to E0.
Okay.
That's right. So on the one hand, we have this commutative product on the cohomology. There's also another structure in the story, which is that the tangent bundle to the parameter space is naturally embedded inside of E. And to understand that, you have to know a tiny bit about how you make deformations of these quantum field theories. But the way you make the deformation is, if you think of the quantum field theory as being, let's simplify by imagining that this quantum field theory is actually defined by some action principle. Then the way you make a deformation is to deform the action a little bit. And the kind of deformation that we consider here is you deform the action by literally adding one of these chiral operators, one of the operators in the Q cohomology. Given such an operator, you act with two supercharges on it to produce this thing called the descendant O2. Anyway, it's produced in some linear wave from O, and then you integrate that over the whole space-time. So you deform the action just by adding this operator. And so all the deformations we consider are obtained in that way. So that means that the tangent vectors to the parameter space are all coming from elements of E. So we have a map from the tangent space to C into E. And so putting these structures together, on the one hand, I have a map from TC to E. On the other hand, I have a map from E to the endomorphisms of E. So if I put that together, I have a map from TC to the endomorphisms of E. And because this product is commutative, so call that phi. And because that product is commutative, this phi obeys this relation, this kind of commutativity relation. So another way of saying that is that this bundle E that just comes from the operators of the theory is not just a holomorphic vector bundle, it's actually naturally a Higgs bundle over the surface. Okay, so whenever we have a surface defect in a 4D n equals 2 theory, we naturally get a parameter space with a Higgs bundle over it. Okay, so now, so far all that was without turning on this equivariant deformation. Now suppose I turn on this equivariant deformation. So one of the important things about this equivariant deformation is that the supercharge Q gets deformed to a new supercharge, which I'll call Q epsilon. And Q epsilon, the original Q is squared to 0. The new equivariant supercharge Q epsilon, it squares not to 0, but to a rotation around the origin. And in particular, the operators that are away from the origin can't be invariant under this Q epsilon. Okay, again, this is parallel to what I said in 3 dimensions, where we got restricted to the axis. Now we're going to get restricted just to sit at a single point. So, and I'll let E epsilon be the cohomology of this deformed supercharge Q epsilon. So now, even if I have two operators, say O and O prime, which would be Q epsilon invariant when put at the origin, when I build their product, this O of Z, O prime of 0, that won't be because the Z is not a fixed point. So that looks like an obstacle to defining any kind of product structure in this story. So before we had a product, now we've turned on this equivariant parameter and the product seems to be destroyed. Well, okay, we can try to restore the symmetry by averaging over the circle. But as it turns out, that's still not invariant under the deformed supercharge. So once we've turned on this equivariant parameter, it seems like we have no way of multiplying the operators anymore. So to multiply them, we have to be able to put them at distinct points. But once we work equivariantly, there's no room in 2 dimensions to put them at distinct points. And so it looks like what we have is now just a vector bundle over C, nothing else. So we had a Higgs bundle and now we've deformed it and now we just have a vector bundle.
Yeah, but you have something like, epsilon connections or whatever.
Well, right. So that's what I'm about to say. So what I want to explain is how we get an epsilon connection in this context.
Yeah.
So we just said that we don't exactly have the product structure. Now, another thing we can consider is perturbing the theory by, as we said, by adding to the action the descendant of this chiral operator O. Now, suppose we do that. Now let's look at this. let's compare the operators of the perturbed theory to the operators of the original unperturbed theory. I suppose we start with an operator, say O prime again, which was Q closed in the unperturbed theory. Well, after we make the perturbation, it's not necessarily Q closed anymore. So one way of understanding that is that when we add to the action this integral over the whole space, that integral over the whole space will run over even the points where I've inserted operators. So, for example, where I've inserted O prime. In defining the correlation functions of the perturbed theory, I have to deal with these integrals, which include operators placed at coincident points. So the usual way of dealing with that, of trying to define the perturbed theory, is to cut out a little disk. You say, okay, well, we'll integrate over the whole space, but we'll cut out little disks around the places where we've inserted operators. But that regularization spoils the Q invariance. So after you make this deformation, the operators which were Q closed are not necessarily Q closed anymore. So said otherwise, this bundle of operators, when epsilon is not turned on, doesn't carry a natural connection. But these two problems, so I just described two different problems. One having to do with the deformation by adding epsilon, and one having to do with the deformation by adding an operator T. And those two problems, you can make them cancel one another. So if we do both things at once, we perturb by adding this operator O to the action, and we also turn on the omega background with some parameter called epsilon, then we have these two individual things. We have on the one hand the chiral ring product, and on the other hand the just displacing the operator from the perturbed theory, from the unperturbed theory to the perturbed theory. Each of those separately is not Q epsilon invariant, but the combination actually is, if you take this combination. And so said otherwise, this field theory, once you turn on the omega background, it does not have a product structure anymore. It's not a Higgs bundle anymore, but it does carry the natural deformation of that, which is a connection. The way I wrote it here, it's kind of naturally an epsilon connection. So it's epsilon times a connection. If you rescale it by 1 over epsilon, you get an ordinary connection. So what am I saying? So this is a strategy for explaining in kind of quantum field theory terms why there's a deformation, which at epsilon equals 0 you have a Higgs bundle, and at epsilon not equals 0 you have a bundle with connection. In other words, you have a parametric family of ODEs with which degenerates to a Higgs bundle as epsilon goes to 0. So that's the structure that was in the equations I was writing earlier. And what I'm trying to explain is the strategy for seeing why that deformation arises kind of naturally in quantum field theory terms from this from working circle equivariantly in the 2D 4D system. So this point of view, of course, is kind of close to something that's been pursued before, particularly in the context of pure two-dimensional theories. And so many people have thought about this, particularly in kind of categorical language. There's a description of how this deformation happens by Ezra Getzler. That's somehow close to what I'm saying here in quantum field theory terms. But so to develop it exactly in this 2D 4D context, and to see that we get exactly the ODEs that are expected is some work in progress with myself and Ali Shepard. Okay.
Will it be ODE or maybe difference equations?
Right. So far, I'm really just talking about the case of ODE. Now, there is some extension of it. I think that's actually the next thing I was going to say. There is some extension of this story that covers difference equations. But in this initial work with Shepard, we're just working on the case of the ODEs. but I did want to say a few words about the story of difference equations. So how do difference equations get into the story? So the way that difference equations arise in this picture is if we consider a surface defect theory slightly different from the ones that we considered so far. So far I considered surface defect theories which didn't support any extra symmetries living on the defect itself. But it's very natural to do that, to consider a surface defect theory which supports some extra so-called flavor symmetry. So it has a group acting on it, and the simplest thing to imagine would be to have the group like U1 to the n, or even say just U1. Then in that situation, you have a parameter space of slightly different nature from what we talked about so far. You have what's called the twisted mass parameter. So you think of it as working equivariantly, now not for rotations or anything, but for the this extra symmetry that acts on the surface defect. So then you have the equivariant parameter for that, and that's called the twisted mass, and I'll let C be that parameter space. In that case, there's an analogous story, which is not exactly the same, because in this case, the deformation is not exactly descendant of a chiral operator. And so the story, instead of being a story of a Higgs bundle deforming to a differential equation, there's a parallel story of a multiplicative Higgs bundle deforming to a difference equation. And there, yeah, so there I haven't yet seen the analog of this story. But okay, so what I want to say about it is just that, so now you could ask, in this context, you know, from various different directions, people have written down the appropriate difference equations. And you could just ask, okay, does the dictionary that I told you in the 2D, 4D systems, does that dictionary continue to hold in this setup? Meaning, is it still true in particular that the Stokes phenomena, now we're talking about Stokes phenomena for a difference equation rather than for a differential equation. You could ask, is it still true that the supersymmetric particles of the field theory with flavor symmetry correspond to the singularities in the Borel plane now for the difference equation rather than the differential equation? And okay, so in short, it appears that the answer is yes. And again, it's been, you know, in hindsight, it's been studied in various directions by different people, particularly in the paper of Chakotay, Gayotto, and Vafa on sort of higher dimensional versions of TT-Sara geometry. But recently we studied it just in some specific examples with Albert Grassi and Chen Yu Hao. So the most basic example you can think of is just a two-dimensional theory, just a pure two-dimensional field theory, but now with a flavor symmetry. So the example would just be the theory of a single chiral multiplet. So just a free theory with n equals 2, 2 supersymmetry, no gauge symmetry, just matter, but with a U1 flavor symmetry. And then the difference equation that appears is this equation, which is roughly speaking solved by the gamma function. It's like the difference equation. If epsilon was 1, this would be literally the difference equation of the gamma function. And so then the story about Stokes phenomena just boils down to the usual Stokes phenomena for the gamma function. So it's known that for the gamma function there are Stokes phenomena just along two rays. There's literally two poles in the Borel transform. Oh no, sorry, I take it back. There's two rays. I guess each one has some infinite chain of poles. But there's two rays, and those two rays correspond exactly to the expected two supersymmetric particles in this quantum field theory. Then a sort of slightly more interesting example is you take a two-dimensional system which comes from taking a three-dimensional system and reducing it, compactifying it on the circle. So then you can take a nice simple free theory in 3 dimensions, reduce it to 2 dimensions. If we take the 3-dimensional theory to be just the theory of a single free field again, then when we reduce it to 2 dimensions, we have a theory of, if you like, infinitely many 2-dimensional free fields. So here the parameter space, rather than C, it turns out to be C star. The relevant difference equation looks like this, which is solved by, again, up to some elementary factors. It's solved by the quantum dilogarithm. And so here, the Stokes phenomena that you get. So the story of the Stokes phenomena in the asymptotic series for the quantum dilogarithm. So we learned about it from the paper of Garufalidis and Keshayev, which spelled out everything very clearly. And when you look at their results, you just see directly that so the Stokes phenomena along infinitely many rays, and the position of the singularities in the Borel plane corresponds exactly to what it should be if you think they correspond to the BPS states of this 3-dimensional field theory. So that's what we described in this.
Yeah, I have to say that, before this paper, Garufalidis and Kashayev, we actually did a much more complicated example. I mean, we actually consider, the index of knots, as arising from the Stokes phenomena in the fully non-trivial theory corresponding to complements of hyperbolic knots, which is infinitely more complicated. So, yeah.
That's true.
This is the work I did with Garufalidis and Gu, which is, essentially calculating the full tower of Stokes constants in a much more complicated example, and actually seeing that this is equal to the indexes of BPS states for these 3D theories. I mean, this is just a toy example compared to what we did.
No, absolutely.
Absolutely, but we are not mentioned, right?
Sorry. Thank you.
In many points, yeah, you see many points. Yeah.
Well, to that I can add that I also did it a very different way with Stavros and Renat did, with a much more general kernel situation.
Is it? Okay, I mean, we should talk
our results were very explicit for that example. I don't know. I don't think that this had been calculated so explicitly by any other people, right?
But is it so? I mean, okay. There's one basic thing that I'm trying to say, which I don't know if it was okay. If it was said in your papers, I definitely.
I gave a talk in a string conference 2 years ago, or maybe 3 years ago, which was called From Resurgence to BPS States, and this program was kind of clearly stated there. And then, with this Chern-Simons theory was just an application, right?
I see, and you said exactly this thing that the BPS states of the.
I say that that the Stokes constants in a resurgence theory would actually count BPS states in more general situations than the one of GMN and the one of n equal 2 supersymmetric theories, and that an interesting example would be Chern-Simons, and then we did the calculation, which is highly non-trivial, and this turned out to be the case in a surprising way. So.
Andy, maybe slightly different question. You have differential and difference equations. Now, do you have a complete list like difference and elliptic difference equations as well?
No. I mean, so yeah. So I think the expectation would be that those would come from taking 6-dimensional systems compactified on in 2 directions, but no, I don't have anything to say about those kind of examples today.
And a different question, Andy, is so this equation here does not uniquely determine the quantum dialog, as I know you know, but do you have a similar system for Q-twiddle, or is there any role of that here, or?
In this part of the story, not directly, right? So yeah, so right. So as you know, in different chambers of the in different parts of the parameter space, you get different versions of the quantum dialogue algorithm, right? And so in one version, you get this this Faddeev quantum dialogue algorithm. In other reasons, you get other versions. Yeah, I don't really know what's the from this point of view, I don't see the physical role of that other equation. But I agree, it's a natural question. Okay. Okay, I guess you're right, Marcos. I'm sorry, I didn't quite realize that you had made exactly this statement. But in retrospect, yeah, surely you did. So you're right. That's so then all I want to say is that here's kind of a very simple example of this phenomenon. Okay. Okay. What else do I want to say? Yeah. So I wanted to say a little more broadly now. So in these coupled 3D, 5D systems, well, okay, maybe I should just, yeah, I think I'll skip my, wild speculations, and I'll just leave this as just a review of the story as it exists so far. Okay. Due to the time, I think I'll stop here. Thanks for your
attention. Okay, all right. Thank you, Andy. Thanks. So now more questions.
Yeah, maybe comment.
Yeah. Go ahead, tell me.
Yeah, I mean, because I'm trying to understand the mathematical side, I understand that you kind of add this parameter epsilon on the quantum field theory side, which is really nice. And mathematical, if you kind of do not deform from Higgs to Higgs bundles for bundles with epsilon connection, and then you have the wall crossing structure on the Higgs bundle side. You have the spectral curve, you have the central charge, you have this BPS invariant. So then the question is how to add this parameter to the existing wall crossing structure, which is determined just from what you know for epsilon equal to 0, say. Yeah.
Right.
Yeah, and so this is why it's called comment, not a question. So we wrote a paper with Maximum, analytic wall crossing structures. I think it's like almost 2 years in the archive, and there we explain how to do that, how to add one more parameter. And we explain this notion of analyticity of the wall crossing structure, which basically the charge lattice and the central charge, and probably you should know that.
Yeah, that much I know.
Yeah, all right. Yeah, but we formulated a general resurgent conjecture, which I am kind of certain that it's true. We illustrated it in many, many examples in mathematics and physics. And basically it says that if you have analytic wall crossing structure, which means you don't have epsilon, yeah, you work just with a spectral curve and all that stuff, but like imagine that you have something like exponential estimates for the growth of BPS invariants. Yeah, not the one, not the quadratic, but just exponential, linear. Okay. And then the analytic, the wall crossing structure is analytic. All right. And so the conjecture says that when you add this epsilon and do the Borel transform and so on, then you get the resurgent series. and most likely the singularities will be at the values of the central charge. At least in the examples, this is the case.
Right.
The singularities of the Borel transfer.
Right.
So then kind of there is a mathematical framework which serves whatever you see when you start with undeformed, without omega background, yeah. You can basically say everything without doing calculation. So that's a comment.
I see. So,
for example, this WKB examples, yeah, it's a special case. 2D, 4D, when you have the defect, which is say point on this on the initial curve, and you move it, and so then you have a product of the base of the Higgs bundle with this curve, and then this is covered.
right.
And the only thing that it's conformal limit, because kind of I was thinking that epsilon, roughly speaking, is equal to zeta, kind of. But this yeah, I should think. But you don't take epsilon goes to 0 there, yeah, because epsilon is fixed. You at the generic point.
You mean in this conformal limit thing? No, that's right. That's
Yeah,
right.
yeah, because epsilon, yeah, what I'm saying, it's rather relevant to the limit zeta goes to 0. And so if you insist that epsilon is fixed, then the arguments which I mentioned, that you start with something which sits at the value of 0 of the parameter, and then you deform, and you know everything this about this Borel resummation or Stokes automorphisms depending on that parameter, it's rather with respect to zeta. If epsilon is large, I don't know. Yeah, but it's well applied to difference case as well. So it's kind of, you know, like in mathematics, you say something and it can be applied to many different examples and models. So
Yes.
this kind of things. Yeah.
Yeah. Yes, thank you.
So more questions.
I had a question or two.
Good.
Let's see. One of them is, so you mentioned that proving Borel summability of these ODE solutions is an obstacle to understanding stuff in a higher rank case.
The higher rank, yeah.
Yeah, and I'm wondering whether there are any special cases, like special cases of ODEs where you know that you do have Borel resummability, because I think that's something. Just like if one wanted to attack this problem, it would be nice to know sort of like what cases are already finished and what cases still need to be understood.
I see. Well, okay. I have no doubt that there are people, maybe even here, who are more expert than me about this. I know a few very isolated examples where we have it, even in higher rank. So like, if you do the kind of higher rank analog of the Airy function, in other words, like, d by dz to the nth power plus z. For that one, you can prove it almost by hand. You can prove the Borel summability.
Yes.
But once you go beyond that, I don't know. Yeah, there must be some other isolated examples for which it's known, but I in fact don't know. The only thing I know is that it hasn't been proved in the generality of like general kind of potentials given by like a quadratic and cubic differential or that kind of thing.
Okay. Let's see. And I guess a related, okay, if nobody else has questions, maybe I can ask two follow-up kind of related questions. Sure. So one question is whether if you had like a machine for generating examples where you could prove Beryl's summability, it would be cool if you could kind of search for ones that are relevant to physics. I was wondering if there's sort of some general guidelines for like
which ones correspond to actual quantum field theories?
Right, which ODEs arise.
I mean, when you write an ODE with meromorphic coefficients on like a compact Riemann surface,
Mhm.
then then it always corresponds to something. Well, okay, sorry, let me say it better. So the ones that we wrote here are, I guess they're not totally general flat connections, but they're what's called OPERs. And so in general, if you write down an OPER, even a higher rank OPER, with meromorphic coefficients on a compact Riemann surface, then that one always comes from some quantum field theory.
Okay.
It's quantum field theory of class S. So you don't have to worry too much.
Cool. Okay. That's interesting. And then the other sort of related question was, you mentioned that these exponential integrals, like these Landau-Ginzburg theories, correspond to exponential integrals, which all satisfy ODEs. And I was wondering if, like, kind of, there's some reference that says specifically what class of exponential integrals you get, and like which ODEs they satisfy.
Yeah, that's a good question. I always find it a little hard to navigate this literature. I mean, for the real baby examples, I can point you to some notes that I wrote when I was trying to understand it. So I'm sure that right, we should be able to find a good reference, at least for like the most basic case is like just polynomials in one variable.
Okay.
Yeah, there. Maybe someone here knows.
That's cool.
What the good reference is. I don't, but I'll try to find one and follow up with you.
That would be cool. Yeah. Once again, it would be cool. Yeah, if you, as you mentioned, if sort of polynomials give good examples, it would be nice to kind of, like there's a big theory, for example, of like, a big classical theory of special polynomials. And it'd be nice to know, say, like which of those correspond to like special Landau-Ginzburg models.
There is a general theory of Gauss-Manin connection, so it's a variation of exponential period, and there are some. But if you want something very explicit, so it's more difficult. Yeah.
Okay. Do all of those? So can you say that sort of you have a general theory of, like you said, this general theory of exponential integrals, and sort of everything covered by that theory also sort of corresponds to a Landau-Ginzburg model?
Landau-Ginzburg is sort of a special case. Yeah, I mean, it's mathematically, again, not with that explicit formulas as Andy present, but mathematically, it's a period. Yeah, you pair the cycle gamma over which you integrate with some closed differential form with respect to the twisted de Rham differential. Yeah. And so then you have this extra parameter, which in the Hodge theory corresponds to, this, when you interpret, when you construct a bundle on this epsilon along the epsilon line. So this corresponds to degeneration of Hodge to de Rham. So you can say some words, it's Claude Sabarot, Saita, Maxim, and Vives Maxim, but it's kind of general thing. It's like theorems. If you want explicit formulas, so probably it's English.
Cool.
Right. That's what I've never been. That's what I haven't been able to find. But they must have been written somewhere.
Okay. That's it. Okay. Thank you.
But I guess in general, it's sort of governed by the Gauss-Manin connection in this case here, right?
Yeah, that's why I said it's rather exponential version, because it's exponential period, not the rational one. Yeah.
So Andy, a question. So you say it's a correspondence, but I mean, how much can you go forth and back? It sounded like a lot like you went from 42D to things on surfaces. I mean,
to the ODE, right?
Yeah.
How much can you go? How much can you go back? I mean, what can I say? The QFT, of course, is somehow that's like a richer object than just the ODE, right? You see the ODE emerge as the equation obeyed by some very specific observables in that quantum field theory. But I mean, I guess you could say that one example of going back is this thing I mentioned, that if you want to know the BPS states of the field theory, you can get them literally just you can determine them if you have some way on the ODE side of finding where the singularities in the REL plane are, right? Which you can do, even if you have no clever idea, you can do it by this Pade-Borel method.
Again, conjecturally, it's pretty clear in many cases, right? I mean, what they are.
Right. So then that translates them to the answer to this question in the QFT, which a priori is a pretty hard question, right? What are the actual BPS states in that quantum field theory?
But there's not a statement that says that the whole theory is sort of governed by these systems of ODEs with these compatibility conditions when the surfaces intersect or some blah, blah.
Yeah, it's not that the whole QFT is contained in this ODE, but somehow what it seems like is that a lot of the sort of supersymmetric part of that QFT is, if you take the QFT and you put it in the omega background, you do this very specific thing, that then, things like the BPS states, the omega background partition function with a boundary condition, those specific things are, the wall crossing and so on, those are captured by some phenomena on the side of the differential equation. Okay. It's not like saying the whole QFT is captured by this differential equation.
No, okay. So thank you. More questions. No, maybe everybody had the chance to ask you questions. So, in that case, maybe let's thank Andy again. It was a very nice talk.
Thank you.
Yeah, we can do it in various reaction ways. It's a little weird in these online talks.
Yeah.
But yeah, many thanks, Andy.
Thank you.
Okay. All right. So see you all.